a question about triangles and the significance of triangles. Well, you can talk a little bit about that. So you have a triangle, and one feature of a triangle is if its corners sort of are just loosely attached, they're just sort of they can deform, they can get the angles can get larger and smaller. One feature of a triangle is it's rigid. And so in other words, once you have a triangle with its three side lengths, there's no way you can kind of squidge it. If you had a quadrilateral, a four-sided thing, then yeah, you might have a square, but if the angles can change, you can just deform it to being a parallelogram. It doesn't have to stay a square. There's a theorem due to a French mathematician in the 1800s that is the statement that the triangle is the only structure that is rigid in that sense. I think that's right. That has this feature that you can't, that if you just define the lengths of the sides, but you don't define the angles, the lengths of the sides alone will define its angles. And so if you make a mechanical structure out of a triangle, there's no way, if you maintain the side lengths, there's no way that the thing can kind of squidge over. So what? Well, if you look at a lot of metal work on bridges and things like that, you'll see these trusses, and these trusses are all made with a bunch of triangles. And the reason for that is exactly this phenomenon. If there were squares, then that square could kind of deform and the bridge could sort of fall over or whatever. But because, you know, steel or something the bridge is made out of is quite, it doesn't, okay, the thing to understand is there are materials like steel that if you take them and you try and bend them, they do successfully bend. But if you try and squash them, they don't. Actually, the best example of that, okay, well, it's true for steel, but it's even more true for some other materials. That, you know, if you try and sort of squash it from the ends, it will be hard to compress it. But if you just try and bend it in the middle, it's much easier to bend. And so that's a reason why it's a good idea to make these trusses where you make these little triangular pieces, because then what's happening is each one of those triangular pieces, it can't change its shape without changing the lengths of the sides, but the lengths of the sides, as you know, have a strong material that can't be compressed there, and so it's prevented from changing the lengths of its sides. So that was a thing that's been known in engineering for a really long time, that if you have these sort of members, these struts and things, that the way you make a strong structure is you have to have a bunch of triangles in it, and that's because the triangle is the shape that doesn't deform if you keep the lengths of the sides constant. So there are other ways of getting sort of fairly stable structures. There's a whole family of fairly stable structures, and I'm not sure I'm going to be able to completely do this justice. There's this was this chap called Buckminster Fuller, who was a kind of colorful character who studied a lot kind of the forms and shapes of things. And he was very big on this idea that he called tensegrity. And the idea there is sort of a generalization of this what doesn't deform when you do certain kinds of operations. And in particular, he was very big on the idea of making geodesic domes, which okay, so if you have a how do you make a dome out of just sort of little struts? What's the best way to make it? Well, let's say you made a thing that was just a bunch of equilateral triangles, just a grid of equilateral triangles. That would just lie flat. If everything is triangles, it just lies flat. If everything is hexagons, it also lies flat, or squares. Those are all things where you can just make sort of tiles that are just pure squares, pure hexagons, pure equilateral triangles, and you can just lay them as a flat tiling. Those are examples of cases where the tiling is flat. But now imagine that, see whether you can do that with pentagons, with regular pentagons. You try and fit those pentagons together. If you fit a bunch of regular pentagons together, they won't lie flat. In fact, if you just start with one regular pentagon, you put other regular pentagons around it, what you'll make is the net of a shape of a dodecahedron. And so what will happen is the only way to have those hexagons these pentagons have their sides right next to each other is to curl them up into a dodecahedron, into a 12-faced object. So if you have hexagons, you can make an infinite flat tiling. If you have pentagons, the only thing you can make is this dodecahedron, which curls up like a kind of discrete version of a sphere. So the idea that exists in geodesic domes and so on is, what if you mix hexagons and pentagons? So it's mostly hexagons, but there are a few pentagons in there. So that means that things can't lie completely flat, because you've got these pentagons that don't let it be completely flat. They add some curvature to the whole thing. Well, there's one sort of famous example of where that's done, which is in soccer balls. Soccer balls have a mixture of, if you look at kind of the stitching on them, they have a mixture of hexagons and pentagons. And they are, and so if they were pure pentagons, then they wouldn't be able to be an approximation to a sphere. They would just be dodecahedral soccer balls, which might be kind of interesting to operate with. But if you want to make a soccer ball that's really a ball, but you want to make it out of more or less flat pieces, you have to mix hexagonal pieces with pentagonal pieces. And the fewer pentagons you have in there, the flatter things will be. So if you want to make a really, really big dome, you would have a bunch of hexagons and not so many pentagons in it. But so this idea of making geodesic domes, for example, out of a mixture of hexagons and pentagons, that's sort of an example. And there's a sense in which there's stability. There's this kind of tensegrity form of stability that you get when there is a sort of a mixture of a force due to gravity, for example, together with the kind of stability of having these struts arranged in a particular way. So that's now, actually, when it comes to geodesic domes, old Buckminster Fuller, came up with them and started building. They've been used for all kinds of things. Famously, there's one at Disney World, and that was an early one that I think Buckminster Fuller did. There's ones in a bunch of different places that they're commonly used. If you see like some kind of radar, or a satellite tracking thing, there'll typically be a geodesic dome that covers it, just because it's a convenient way to make sort of a dome-like thing. So geodesic domes sort of started getting used in the 1950s, 1960s by us humans, but they've been used by other things a very, very long time. So this sort of idea of making a sphere out of these sort of polygonal pieces, well, it's used in biology quite a bit. It's used in, for example, radiolaria, kind of the things, the little tiny organisms that you find in the ocean, where they have a sort of skeleton made of what is it, organosilicates. It's some kind of it's something a little bit like sort of a tiny piece of rock, sort of a crystal that's like a tiny piece of rock, but they tend to form into these kinds of shapes. Same with pollen grains. Same with some kinds of virus coats, although virus coats are often actually icosahedral, for example, rather than forming into these kind of more approximately spherical shapes. But so there are a bunch of places where that sort of idea has been used before. So anyway, but the point is that there's sort of an elaborate analysis that you can make of, given these geometrical shapes, what kind of stability do you get, and to what extent can you approximate spheres and all kinds of things like this. But triangles are really special because they have this property that allows you to kind of make trusses that don't deform in that way. Well, there are all kinds of other sort of clever ideas about using different geometries, making these kind of honeycomb things where they deform in one direction, they don't deform in the other direction, all those kinds of things. Also, people have made molecules that are the shape of geodesic domes or geodesic spheres, so to speak, mixtures of hexagonally connected atoms and pentagonally connected atoms. They're usually called buckyballs, and they're most famously made out of carbon. You can make these different sizes, shapes of sizes of approximately spherical kind of cages of carbon that potentially are useful for things. The more useful form is this thing called graphene, which is kind of a tube-like version of the same kind of idea that has all kinds of interesting properties of being a very good electrical conductor, like a wire, and potentially very strong, and you can kind of imagine using them for all kinds of purposes. But I think the actual the spherical cages also are potentially useful as well.